Hi, and welcome to a crash course into air masses, fronts, and precipitation. So to start, I kind of want to explain that I set this up so that by the end of each section, you should be able to answer these questions. So the first questions that we have are, what are air masses? How are they classified? And why is Oklahoma so susceptible to tornadoes? To start, air masses are large bodies of air that are usually 1,000 miles or more across, several miles thick, and they're all similar in temperature throughout that whole large body of air. We classify air masses according to two things: where they started and the surface of the area they started on. So, for example, they could start in Arctic or tropical regions, Arctic being close to our poles, and tropic being close to the equator, and they can be formed over huge land masses, or we call them continental, or huge bodies of water, which we call maritime. Taking those two things, we put them together to create an air mass name. So if you look at the very top of this picture, the dark blue one we call continental Arctic. That means it formed up near Earth's poles where it was cold and over a large area of land. If you look at the rest of the picture, you can see that a pattern with the names occurs for the rest of the air masses as well. Now, why is Oklahoma so susceptible to tornadoes? Well, that has to do with the air masses. When different air masses, like the warm humid air from the Gulf of Mexico, the warm dry air from Arizona, and the cool dry air from Canada all meet together, they meet in Oklahoma and the surrounding areas. We see this as Tornado Alley. Tornado Alley is also a flat area that provides little interruption, so these air masses can collide together. This collision of air masses causes fronts, which lead to storms and tornadoes. This slide here shows you that black line at the very bottom is actually a cold air mass being pinched in. Its border is not straight. And this causes the rest of the air masses to create a cyclical counterclockwise flow. This flow creates the spinning winds that cause the cloud to spin, and eventually a tornado comes down from that cloud. Now this next section, I want to answer what airlifting is, why it's important, and what some lifting mechanisms are. So airlifting is simply exactly what you think it is, when air is lifted. This is important to know because air resists vertical movement. And if we didn't have vertical movement, then these huge air masses would collide and we'd constantly have storms. In this case, when we have airlifting, it allows for those huge air masses to slide by each other, not always causing fronts and storms. So airlifting is also important because not just the moving of air masses, but it helps with the formation of clouds, precipitation, and the heating and cooling of Earth. So there's a couple different kinds of airlifting mechanisms, but the two I'm going to talk about today are orographic and frontal wedging. Orographic lifting is when air is pushed up due to an obstruction. We typically see this in mountains. This also is the reason why we see rain shadows. As air rises over the mountains, it cools, generating clouds and precipitation. It rains, it storms on the windward side of the mountain. As it goes over the peak of the mountain and starts to descend, the altitude changes. It becomes lower, which means that our air heats up. So the air warms. At this point, the air doesn't hold a lot of moisture. It's warmer, so there is less rain, precipitation. So that's why we see deserts or rain shadows on one side of the mountain, but not the other. Another form of airlifting is called frontal wedging. Frontal wedging is when warm air is pushed up over cold air. This is because the warm air is less dense, so more buoyant. It floats above that cold air. Occasionally, though, those huge air masses in the warm and the cold air collide, producing those fronts. Now, I've mentioned fronts a lot, but what are fronts? Are there different types of fronts? And what's the general weather that comes along with each type of front? Well, fronts are boundaries that separate different air masses. One is typically warmer than the other, and often one has more moisture than the other. They're generally very narrow bands of discontinuity with a front slope at a low angle. The first kind of front I want to talk about is a warm front. So a warm front is a boundary between two air masses that form when the warm air mass is moving faster than that cold air mass. You might see some light rains over a long period of time, and as it passes, it is typically left making the environment feel warmer and more humid. A cold front is the opposite. A cold front is when a cold air mass catches up and runs into a warm air mass. Typically, when we see this happen, we see a lot of rain in a short period of time. We see strong winds, and also in the spring and summer, that's when we see those thunderstorms and tornadoes. In the winter, that's when we see our snowstorms. It leaves behind colder feeling weather and drier air. We also have occluded fronts, and that is when the boundary that forms between the two air masses traps warmer air in the middle. At this point, we see heavy to light rains. There's also one more type of front, and that is called a stationary front. A stationary front is when warm and cold air meet, but they don't move. They stall. That can stick around for days, and we'll see cloudy and gentle rain for a long period of time. Now, how does precipitation form? Like rain. What is the difference between rain, snow, sleet, and hail? Well, there are actually two different processes that can create precipitation: the collision coalescence process and the Bergeron process. The first one usually is seen in warmer clouds, and the Bergeron process is seen in colder clouds. So the way that the collision process works is hygroscopic nuclei are abundant and grow very large, collecting water. Hygroscopic nuclei are a type of condensation nuclei. They're tiny bits of particulate matter, like dust, smoke, salt, and these things attract water more than any other condensation nuclei, which is why hygroscopic nuclei are important. As they grow large, they're no longer buoyant and they begin to fall. But they break apart as they fall because water has surface tension. As they break and fall, they'll collide into other, coalesce or form, combine, and then they'll have surface tension because they'll be too large, break apart, and that pattern will keep repeating itself until it finally reaches Earth's surface. The Bergeron process is when water vapor droplets in clouds supercool, and they form ice crystals. Supercooling is when water vapor will remain in its state until it collides with something solid and then instantly freezes, causing these ice crystals. As these ice crystals hit other supercool, they freeze, growing larger and larger and larger. And the ice crystals actually attract more water vapor. This forces the other water droplets to evaporate and replace the diminishing water vapor in the clouds. This causes a continuity, and the process keeps repeating until these ice crystals grow so large that they have to fall. As they fall, they're hitting other particles and they're collecting more and more. Most of the time, though, they heat up before they hit the ground's earth, resulting still in rain. Now, rain is precipitation that falls as liquid, but in order to be characterized as rain, it must have a diameter bigger than 0.5 millimeters. If you look at the bottom picture, you can actually see how freezing rain occurs. That's when rain falls, but it falls through the air that's below freezing and freezes as it hits the ground. Snow is precipitation that falls as ice crystals. Water vapor condenses as ice crystals. The air temperature below from the clouds to Earth's surface is below freezing, so they remain ice crystals as they fall. Now, sleet is a little different. Snow melts as it falls through the layer of warmth, but it typically remains ice crystals. Sleet, on the other hand, is snow that falls, warms up as it falls, and then refreezes. This refreezing causes it to appear as small, clear ice pellets as opposed to crystals. And the last thing that we're going to talk about today is hail. Hail is precipitation in the form of hard, rounded pellets or irregular lumps of ice. If you look at this bottom picture, you can see that hail actually forms in a cyclical process. It only forms in cumulonimbus clouds. Hail forms when strong updrafts carry rain high into the troposphere. This rain, as it goes higher, freezes into hailstones, which are these balls of ice. They can lower, catch an updraft, and go up again, which causes them to get bigger and bigger. It's also why in some hailstones you can see layers. Eventually, they get too big or they hit a draft of cold air and they're forced down to Earth's surface. Well, that's all I have for today. Thank you for checking this out. I hope you enjoyed this crash course and come back for more.